Week 8 to 9, Boosting Techniques, AdaBoost and XGBoost. Welcome! This lesson explores two powerful boosting algorithms, AdaBoost and XGBoost, using the Pima Indians diabetes dataset. Boosting combines several weak learners to build a strong model. These methods are popular in data mining and machine learning. We will start by loading real-world health data, prepare it, and finish by using boosting to predict diabetes. Let us begin. Running the cell now. First, let us turn off any distracting warning messages. This helps our output stay clean and easy to read. Import NumPy as NP. We set the random seed to 42 for reproducibility. Running the cell now. This code sets a random seed and suppresses warnings to ensure consistent, clean results throughout the lesson. Although no output is shown, this setup is crucial for reproducibility when training AdaBoost and XGBoost models on the diabetes dataset. It ensures that any results or metrics you see later are stable and easier to interpret. Data setup. We will use the Pima Indians diabetes dataset. This famous medical dataset helps us predict diabetes based on health measures. Running the cell now. We import pandas for data handling. The dataset is loaded directly from a public URL. Columns are named to make the data readable. We read the data into a data frame. We print the shape to see how many rows and columns we have. We display the first few rows to peek at the data. Running the cell now. This output shows our dataset has 768 rows and 9 columns, confirming a good sample size and all expected features are loaded. The first 3 rows give a glimpse of each variable, including health metrics like glucose and BMI, along with the binary outcome column which indicates diabetes presence. This initial data inspection sets the foundation for understanding and preparing the dataset before we start applying prediction models. Check for missing or suspicious values. Zeros in variables like glucose or BMI can mean missing data. Let us check how many zeros appear. Running the cell now. Now we see how many zeros may hide missing values. We loop through columns that should not be zero, like glucose and insulin. We print the number of rows with zeros so we know if we need to fix them. Running the cell now. This output highlights how many zero values appear in key health columns, which likely represent missing data rather than true zeros. Notice that skin thickness and insulin have particularly high counts of zeros, signaling significant missingness to address before analysis. This step ensures we identify suspicious values early to improve data quality and model reliability. This line is a comment explaining the upcoming data cleaning steps. We import the NumPy library to use its nan value. We start a loop over specific columns to clean them. In each column, zeros are replaced with nan to mark missing data. We fill these missing values with the median of the column. Finally, we print counts of missing values to verify the cleaning. Running the cell now. The output shows that there are no missing values remaining in any column after replacing zeros with nan and imputing with median values. This confirms the code successfully addressed suspicious zero values in key health variables, ensuring the dataset is now clean and ready for analysis without gaps. Explore outcome balance. Let us check how many patients have diabetes versus those who do not. Running the cell now. We print out how many positive and negative cases are in our dataset. This helps us spot if the classes are balanced or not. Running the cell now. Here we see the distribution of the outcome of variable, showing 500 patients without diabetes, 0, and 268 with diabetes, 1. This imbalance highlights that more patients do not have diabetes, which is important to consider when building and evaluating predictive models for this dataset. This comment indicates that we are making a quick plot to check the class balance. We import the matplotlib.pyplot library for plotting. We plot a bar chart showing the counts of each outcome class using different colors. We label the x-axis to indicate what the classes represent, diabetes present or not. We add a title to the plot to explain what it shows. We display the plot so we can see the visualization. Running the cell now. This bar plot shows the distribution of patients with and without diabetes in the dataset, with 2 bars representing the counts for the 0, no diabetes, and the 1, diabetes. We notice if the classes are balanced or skewed, which is crucial for modeling decisions. The intent is to quickly understand outcome balance before diving deeper into predictive analysis. Let us split our data into features and the target. The features go into X and include the health measurements. The outcome column, with diabetes status, becomes our target variable. Running the cell now. Here, we've separated the features from the target variable, outcome, which indicates diabetes presence. This step sets up the data for analysis by isolating the key column we want to explore, the balance between patients with and without diabetes. Although there's no direct output, this split is essential before checking class distribution and model training. Now we split the data into training and testing sets. 80% will train our model and 20% will check performance. We use a random seed for repeatable results. Printing shapes makes sure our data split worked. Running the cell now. Here, the code splits the dataset into training and testing sets, with 614 patients in training and 154 in testing, each having 8 features. This ensures we have a balanced sample to evaluate our model's ability to distinguish patients with and without diabetes. Notice the 80-20 split, a common practice to maintain enough data for learning while reserving some for unbiased testing. What is boosting? Boosting combines several simple models, also called weak learners, to build a smarter one. Each learner focuses more on points that past models missed. Boosting often improves prediction accuracy in real-world tasks like health or finance. Running the cell now. Let us set up AdaBoost, which means adaptive boosting. We import the AdaBoost classifier from scikit-learn. We choose 50 base learners for this experiment. We train, or fit, the AdaBoost model on our training data. Running the cell now. This output shows that the AdaBoost model was successfully created with 50 weak learners, as specified in the code. Notice how the constructor confirms the model's configuration, indicating readiness to focus iteratively on misclassified points, demonstrating the core concept of boosting. This section is about making predictions with AdaBoost and checking accuracy. We import the function to calculate accuracy from scikit-learn. We use the AdaBoost model to predict labels for the test data. We calculate how accurate these predictions are compared to the true labels. We print the accuracy score formatted to 2 decimal places. Running the cell now. This output shows that the AdaBoost model correctly predicted 75% of the test cases, demonstrating a solid accuracy. Notice how this score reflects the combined strength of multiple weak learners focusing on difficult data points, which is the core idea behind boosting. This confirms that AdaBoost can improve performance by iteratively boosting weak models. What about XGBoost? XGBoost is an extremely popular and powerful boosting method. It was used to win many data competitions. Running the cell now. Now we set up XGBoost, which stands for Extreme Gradient Boosting. We import the XGBoost classifier. To avoid some warnings, we set label encoder to false and choose log loss for evaluation. We fit the XGBoost model to our training data. Running the cell now. This output shows the default configuration of the XGBoost classifier after fitting it on the training data, highlighting many parameters still set to none or defaults. Notice that key hyperparameters like max_depth, learning_rate, and n_estimators are not explicitly set here, which means XGBoost will use its built-in defaults. This reinforces the lesson point that XGBoost is a powerful, flexible model ready to tune for improved performance in competitions. This section performs prediction and evaluates accuracy for the XGBoost model. Predict diabetes presence for the test dataset using the trained XGBoost model. Calculate the accuracy score by comparing true labels with predictions. Print out the XGBoost model's test accuracy for review and comparison. Running the cell now. The output shows that the XGBoost model achieved a test accuracy of 0.71, meaning it correctly predicted 71% of the test labels. This demonstrates the model's effectiveness in classification tasks, highlighting why XGBoost is a powerful and popular choice in machine learning competitions. Notice this accuracy as a key metric to compare against other models and understand XGBoost's performance on your dataset. Plot the feature importances from the trained XGBoost model. Import the Seaborn library for creating the plot. Get the feature importance scores from the XGBoost model. Get the list of feature names from the dataset columns. Create a horizontal bar plot showing feature importances with a blue color palette. Add a title to the plot to describe it. Display the plot visually. Running the cell now. This plot shows the relative importance of each feature as determined by the XGBoost model, highlighting which variables most influence predictions. Notice how some features stand out with much higher importance scores, reflecting XGBoost's ability to identify key drivers in complex data. This visualization helps us interpret the model's decisions and confirms why XGBoost excels in feature selection during boosting. Try removing the most or least important feature, then retrain XGBoost to see if accuracy changes. Which model won? Compare the AdaBoost and XGBoost accuracy scores from above. Notice which model is better on this dataset and think about why. Running the cell now. Comment indicating we are creating a confusion matrix for the XGBoost model. Import confusion_matrix and confusion matrix display from sklearn.metrics to help generate and display the confusion matrix. Calculate the confusion matrix using the true labels and predicted labels from the XGBoost model. Create a display object for the confusion matrix with appropriate class labels from the model. Plot the confusion matrix using an orange color map for visualization. Set the plot title to indicate this chart is the XGBoost confusion matrix. Show the plot so the confusion matrix is rendered on screen. Running the cell now. This confusion matrix shows how well the XGBoost model classified each class in the test data, with darker oranges indicating more correct predictions along the diagonal. Notice the concentration of high counts in the diagonal cells, which reflects the model's accuracy and its ability to correctly identify key classes. Comparing this to the AdaBoost results helps confirm which model performs better overall on this dataset. Now you are the health expert. We show the features for one patient. You guess whether they have diabetes. Type 0 or 1 based on your reasoning. We use XGBoost to make its own prediction. We show what XGBoost thinks. Now compare your answer to the model. Did you both agree? Running the cell now. This output shows a single patient's health data and the XGBoost model's prediction for diabetes, illustrating how the model makes real-world decisions. Notice the key features like glucose, BMI, and age, which heavily influence the prediction outcome. This interactive step helps connect model accuracy scores to actual predictions, reinforcing why XGBoost might be the better model on this dataset. Try with new samples, and challenge a friend to see who does better than XGBoost. If you are finding this helpful, please like and subscribe for more hands-on tutorials. Tips for boosting success. 1. Always check your data quality first. 2. Avoid overfitting by limiting tree depth and tweaking estimators. 3. Try more or fewer estimators for other datasets. 4. Tuning learning rate can improve results. Practice often with new datasets to build experience. Running the cell now. This is a quick challenge prompt about tuning the XGBoost learning rate. We create an XGBoost classifier with a specified learning rate of 0.1 and some fixed settings. We train the model using the training data, features and labels. We evaluate the model by predicting the test set and measuring accuracy. Finally, we print out the accuracy score with the specified learning rate. Running the cell now. This output shows the accuracy of an XGBoost model with a learning rate set to 0.1, achieving 72% accuracy on the test data. Notice how adjusting the learning rate directly impacts model performance, demonstrating the lesson's tip about tuning this parameter to potentially boost results. This step encourages experimenting beyond default settings to find the best balance for your specific dataset. Recap. You loaded and cleaned a real medical dataset. You ran both AdaBoost and XGBoost to predict diabetes. You visualized features and model results. Great job exploring boosting techniques in Python. Running the cell now. Thank you for joining this hands-on lesson. Keep practicing by trying boosting on other datasets. Subscribe on YouTube for more beginner-friendly, practical data mining guides. Running the cell now.